being here at this at the very end of the conference, which was really stimulating. I appreciate very much this idea of citing old works and building connection. I think we should keep this in mind for the next conference. So, yeah, I will talk about, I've been sleeping for 25 years, and then I woke up, as Raymond was describing before, so we are now reanalyzing the old models and try to understand if we missed something 25 years ago, and if this can explain some of the features that we observe in deep learning, machine learning in general. So this is our research group, and as you can see, we have a huge gender problem. But so the kind of networks I'm going to talk about are of this form. Everybody uses this picture from the web, and so I will try to analyze the space of solution in the weight space of this multi-layer network in context in which we can actually do calculation. I don't think I have to review how this network works. It's just a composite function, and the dynamical variables are the weights over the link. And we want to find the weights such that on a given training set, a given input-output mapping is implemented. And this is where deep learning has shown a lot of progress recently, and so this is the context of supervised learning. Okay, so in order to perform learning, what we typically do is to minimize a cost function, and this cost function just can be of different forms. The most, say, natural one is just the number of errors. One would like to find the W's such that on the examples, the network does not perform errors. Or an alternative is just the so-called mean square error, where one tries to minimize the output activity of the network with respect to the desired one, or even another one is the cross entropy loss function, in which one interprets the output as if it was a probability instead of an actual output. And the nice thing about these last two cost functions is that you can take derivatives and you can perform stochastic gradient descent, whereas the first function is cannot be derived. Okay? So this is the general setting. So what I would like to describe is, in the last 25 years, this network have evolved a little bit, and this has changed the rule of the game. So something has changed. It's not always the same things that are happening. So the choice of the loss function has been tuned. The transfer function has been selected. Now we mostly use a ReLU function. The learning dynamics has changed. People are using, for instance, stochastic gradient, which at the beginning was introduced in order to speed up full gradient, but later it turned out that this had some beneficial effects in terms of convergence. And then, of course, the architecture have changed. Now we have many, many layers, and then some of these layers perform pre-processing. So there are many, many things that enter into the game. So in order, in this complicated setting, in order to understand what happens, what the way we decided to follow is just to analyze piece by piece, which is what is going on. What have these modifications changed in the game? Okay, so the idea is that we start with the neural network, of the 90s, which is very similar to a spin glass, so where we have a lot of minima and a very complicated landscape. And then, there's this evolution that happens. And so the idea that essentially all these modifications have changed the landscape in such a way that, some relevant minima have acquired a more important role from the point of view of the learning dynamics. This is more or less the conjecture. Okay? So first of all, which kind of network do we study? Well, we study this type of network. I apologize, they're very shallow, and these are just the network that we are able to analyze. And these are very far from real network that look like this, where each box here is much more complicated than one of the networks that I've just shown you. But from the point of view of the learning and optimization, there's a lot to understand already at this level, because these are highly non-convex problems, and so there are many things that we can extract already with one hidden layer. Okay. So as Remy has already described, one can analyze the learning problem as statistical mechanics problems in which one consider the loss function, so the number of errors as an energy function, and then one would like to estimate the Boltzmann weight given this error function, such that when you take the effective temperature to 0, beta to infinity, this probability distribution concentrates on the minimum of the loss and will tell you something about the learning capability of your device. So this is a very standard thing that we have been doing since 40 years, in fact. Now, again, if one takes the beta going to infinity limit, one can study which is the space of weights, the subspace of the weight space that correspond to perfect learning, and study the geometry of the space of solution. Okay? And this was done, again, many, many years ago, so this is a kind of overview. This is called the Gardner volume. And if one, for instance, if one takes a machine like this, which is called the committee machine, it's a non-trivial, already non-trivial one hidden layer neural network, one finds a diagram like this, that if the ratio of the number of random patterns to the number of inputs is below a certain value, the space of solution is connected, it's replica symmetric. And then well, it's replica symmetric, say. And then if above a certain value of alpha, the phase space breaks into non-ergodic components in a RSB scenario. So this was known already many, many years ago. And oh, this is full RSB actually. So, but depends on the architecture. Okay. And then there was a very nice work that Remy forgot to mention by Remy and Domenico Kane in 1940, in which they analyzed the fine structure of these domains, and so they were able to associate internal representation to the nature of the volume and so on and so forth. So we knew a lot of things. Okay, now the same thing happens in an even simpler object, which is the simplest object we can study, which is the so-called binary perceptron. It's just one single neuron with binary weights. Already this problem is super complicated because it's highly non-convex. It's a real spin glass. And so now instead of talking about volume in the weight space, we have to talk about points on the hypercube. So we talk about entropy of the ground states. But again, the phenomenology is very interesting. So now, so let's start with the binary perceptor, and then we go to the continuous networks. So in the binary perceptor, what we know that there is a critical capacity. I mean, there is a maximum number of patterns that can be stored, random patterns. And what is interesting is that the space of solution, the geometry of the space of solution is particularly simple because all the ground states are point-like, so it's a golf course. And I think Nike also discussed a bit about this model. Now, in a situation like this, we all expect that learning is a hard problem, okay? Because this is a 1 RSB object in which you have this point-like solution, a lot of metastable states, and also above this critical value, there's even freezing in temperature, so it's a really, in principle, it should be difficult to learn. But in fact, this contradicts some empirical evidence. So this is, a kind of a glassy object, which actually, when you try to train it, if you use simulated annealing, you get stuck. If you use simulated annealing, you don't even improve with respect to random initial condition. You are not able to go down for large n. But as soon as you modify a little bit your learning algorithm, it starts to work. And if you numerically observe what happens is that all the learning algorithms end up in very strange minima that are completely different from those that you would have predicted from the equilibrium analysis, the statistical mechanics analysis. And the nature of this minima, so we have been studying this since some years, can be revealed by trying to study if in this problem there exists some subdominant, but yet there exist regions that are very dense in solutions. So the idea is, in this problem, can we find regions that contain an exponential number of solutions, which, however, are subdominant compared to the point-like solution which dominates the Gibbs measure? And so this can be done by defining what we call a local free entropy, which is nothing but a function that counts how many solutions you have at a given energy within a certain hypersphere of radius d. And if you do this, you do find that in the binary perceptron there exists this strange object which was overlooked in the 90s. And that algorithm tend to end up exactly in this minima. And in this picture, one can appreciate the fact that this is distance and this is the density, the log of the entropy. And so at small distance, the density is really very, very high because this curve overlaps with the log of the binomial coefficients, which means that essentially everything is a solution, all the configurations. So it's a super flat region in this golf course. And recently we have been doing some exercise with first and second moment methods, and for a particular version of the binary perceptron model, we can show that in fact there exists an exponential number of pairs of solution at arbitrary distance x below a certain threshold. So somehow this statistical physics calculation can be proven to be correct. Okay, let me skip this because I don't think I have a lot of time. Let me just say that if one uses this new function, the local entropy, to build up a simulated annealing algorithm, indeed one finds, as expected, this dense minima. So everything is very reasonable and works. Now, what happens if we go back now to multi-layer networks with continuous weights? What happens is that now we have, instead of high local entropy region, we have to look for wide flat minima. So regions in the weight space that, like in a lake, we have to find a lake in the weight space, a huge lake. And so we have to look for wide flat minima. Again, in this scenario, if one analyzes the very same object for which the replica analysis gives these results, if one analyzes the large deviation properties of this problem, so if one analyzes the checks for the presence of high density regions, indeed one finds that they do exist for any value of alpha. Okay? And one can show that different type of algorithms actually find different type of solutions. Some of them, this blue one, are those that are revealed by this large deviation analysis and would have been overlooked by the statistical physics and analysis. Okay? So these are three different algorithms. They all work in a certain regime of alpha, but only one algorithm actually goes into these very flat regions. Okay, first of all, this is it's kind of an exercise, but it's interesting. Are neural networks special? Well, in a sense, yes, because I can give you, for instance, an example for which these wide flat minima do not exist. If you take a parity machine in which in the output node you take the product instead of a sum and a threshold, so you take this parity function, then for this problem, you can show that these rare events do not exist. You don't have these wide, dense regions. And in fact, if you try to use this device to perform any form of learning, you fail badly. So now that we've understood, at least for these kind of devices, that this could be the scenario, can we use it to build algorithms? Okay? So the idea, in a sense, is that we have defined a measure that concentrates on this wide minima, and the idea, can we tune the distance that defines this measure in such a way that we can focus and then reach these dense regions. And you see, we start with a very rugged landscape, and by introducing this local entropy or local volume, by the way, it's not local, it's order n, so I'm sorry for the choice of the word was really bad. But so we can, in a sense, make the surface more smooth and find a solution. Now, the trick is the following. One can rewrite the free entropy by, this is why here is the effective temperature associated to this free entropy that we have introduced. And if you take this y integer, you can rewrite the partition function as a sum over all configuration of a centroid of these dense regions, and then a trace over all the replicated systems times this E2, this energy function here. So if you take y integer, essentially we can show that you can rewrite the Boltzmann weight of this energy function as the Boltzmann weight of a set of y real replicas of the original system coupled to be at a given mutual distance. So this replicated system naturally focuses on these rare dense regions. And so once you realize this, then it's immediate to define as many algorithms as you want. And in fact, okay, so this is effectively what you do. So you instead of studying just the normal energy function, you study y replicas of the original problem plus a coupling between them. And you want y to be large because you want to select those regions that are the most dense, okay, that have the highest entropy or the largest volume, okay? So it's immediate to write replicated cavity algorithms, for instance, and they work pretty well. Just you take the replicated factor graph plus this distance constraint and you run a message passing algorithm on that. Or you can, so you can do replicated belief propagation, replicated simulated annealing, replicated stochastic gradient, and so on. And all these algorithms turn out to work very well. Okay?
Sorry, how do you choose gamma?
Okay, gamma is the distance, it's conjugate to the distance. Okay? And the idea is that you begin with a small gamma, so large distances, so that you sample from a large region, and then you change it so that you focus on smaller region, but by following, you know, this wide minima.
So you increase gamma to the
Yes, yes. And okay, so this kind of trick has been used also in deep learning, and it's called Entropy HGD. And it's also been parallelized. And it was also used before our work by a group in New York, but they did this, you know, not really with the understanding that we have now. It was for with different kind of motivation, but you know, it kind of works. I want to mention just this little algorithm that we have found, just to tell you that just by introducing a little entropic ingredient, you can make a very simple algorithm. You can make it become effective. So for instance, there is an old algorithm for training this kind of network, which is called least action learning. And the algorithm is very simple. It goes as follows. You present an input. If there is no mistake outside, you do nothing. If there is a mistake, you look for the hidden nodes that has the smallest local field, and then you change it. So you do the minimum change that, you know, tries to improve the performance of your, and if you do this, kind of it works, but it ends up in very bad minima. Actually, we can show it ends up on the boundary of these regions. But if you now replicate it, and so you do what we call ELAL, like the airline, then this algorithm turns out to be very effective and find very dense regions. So you have a very greedy process, and with a little ingredient, you can actually make it effective in finding interesting minima. I hope.
What do you mean by it doesn't work?
I mean, it works, but it finds, let me say, bad minima, in the sense that it finds minima that have are very narrow, but they're not isolated. They're just on the boundary of this dense region. They have bad generalization performance. Okay, and the idea is the reason is if we take many copies of this algorithm, the only way that you can couple them and have them to converge to the body center of this region is only if they are on the boundary, right? If they were isolated, it would not be possible to make them converge together. You see what I mean?
So you're saying that the boundary of this region is better from the boundary?
The precise geometry of this region it's very difficult to analyze. We have really no idea of how it looks. Okay, so this is just a numerical result. And this is, we can compute Hessians to check whether the volume that we can compute using replicas connects also with the local flatness. And in fact, we can show that, if you use an algorithm that targets these dense regions, you find a small spectrum, which is peaked around 0, whereas if you use a very greedy algorithm, you find a wide spectrum. Okay, and also we have been able to show that a lot of people use stochastic gradient plus cross entropy, and cross entropy contains an effective temperature. If you do a slow cooling of this cross entropy, you actually end up in very dense regions. Okay?
Is the Hessian where? During the
No, at a fixed point, you find a solution. Well, because I mean, it's not a perfect. This function here are you compute the Hessian using, say, mean square error or the cross entropy, so it's not perfectly flat. Okay. Yeah. You can also have negative. You can have zero error and still minimize your function. This is what I'm saying. This is not the error function. But also because you cannot compute the Hessian of the error function. It's a very trivial thing, don't worry. And one thing which is interesting is that if you just try to correlate the size of this, the flatness and the size of this wide minima with the generalization error, you find that they actually are correlated. So the wider is the minimum, the better is the generalization performance, at least on some numerical experiments. Now, how many minutes I have? 3, 2, 5. Okay, so I skip over this. One can show that by using stochastic synapses, stochastic ways, one can also address these kind of regions. And also by using, I apologize for this, quantum annealing. I apologize in the sense that I'm not really in the business of quantum computation, but one can show that quantum annealing works for this kind of system because quantum fluctuations are focus on these dense regions because the wave function can delocalize. And so you have the kinetic energy term, which it's favored by the existence of these wide regions. And by the way, the only reason why in the European project, physicists, this new European project, ELLIS, physicists are present is because of quantum machine learning. So now we are trying to insert also statistical physics. Okay, so this is just a parenthesis. Okay, so let me skip this and let me go to, there's some initial application of these ideas also to unsupervised learning, but let me go back to conclude to the evolution of neural network. I want to just give you two results. The first one has to do why people are using the cross entropy. Well, the reason is that one can show that the ground state of the local entropy loss function corresponds to the rare dense state of the error function, at least in the models we were able to analyze. Okay, so if you find use the loss function, the cross entropy function, you find the ground state, and then you use a Franz-Parisi calculation. You check how many solutions of the zero error problem you have around the ground state that you have found. You find an exponential number of such solutions. So you end up in a rare minima of the original cost function. So this, it's not surprising because cross entropy introduces a kind of robustness. So it's not totally surprising, but it's something clear. So this is why people are using cross entropy. It leads you to this wide minimum. And the other thing we have recently analyzed, and Enrico Malatesta has presented a poster, and I want to mention this briefly, is that it's another aspect of the evolution of these systems. Why people are using ReLU functions? Well, they're using ReLU functions, so we have reanalyzed the problem, the storing problem with ReLU functions. Now, since the ReLU functions are always either zero or positive, we have to choose this last layer with random plus or minus weights, but this is just a technicality. So one can study this model with ReLU transfer function in these nodes here, and we want to study what happens as k goes to infinity, okay? And well, the idea is that, well, if you use a sine activation function, you find a capacity that diverges with a number of hidden nodes. I mean, it doesn't diverge very quickly, it's the square root of log of k, but still it diverges. Whereas in the case of ReLU, the capacity remains finite. So you don't gain by increasing the size, the width of the hidden layer, okay? This was surprising. I'm not saying it's particularly relevant or what, it's just, for me, it was just surprising. But what we were looking for is actually, okay, this is, I don't think I have time to explain the picture, so let me just say it in words. We found that the kind of ground state you find using ReLU functions are denser than those that you would find using the sine function. You end up in more dense minima. Okay, and in fact, if you do this little experiment, so you find your this could also be done analytically, but we were too lazy, and so we did just a numerical experiment, but it can be done. If you train one of these networks with a sine function or with ReLU function, and then you perturb the input, so here is the noise you put on your training set, and here are the errors that you make in output, you see that the ReLU function is much more robust compared to the sine function. So all these things to say that there are all these ingredients that have to do with the landscape and the architecture. Now, the next step is to analyze the role of the depth, okay? But there are all these ingredients that connect to the out of equilibrium, to the rare state properties of the of this network. So it seems to me that there is a lot to understand. So this is a very empirical field in which a lot of results are accumulating, and so we need to understand what is relevant and what is not relevant. So just to conclude, I would like to mention 3 problems that I find particularly fascinating. I mean, I have nothing to say about them. I just want to share. One is some recent papers about the connection between causality and invariance in data. So if you have data sets and you look for invariant patterns, then you extract information about causality. And this corresponds to a learning problem which is highly non-convex, so it's very glassy. So another thing that I learned recently is that if you do a multi-stage problem in which you want to optimize both the architecture and the weights in a 2-stage problem, so you find not only the optimal weight, but also the optimal architecture, then in the meta-parameters which characterize the architecture, again, you have a very glassy landscape, okay? And then there are all, a lot of problems related to what happens when you put constraints on your network that, in order to make it more realistic, and this is, again, a problem which connects a lot with glassy systems. So it seems to me that there is a lot new things to do, and the first one in particular is, potentially very far-reaching from a computational point of view. Okay, I'll stop here.
Are there any questions? Many. Okay, so Giorgio.
Yeah, so maybe, okay. So, I mean, I cannot enter into the details. I didn't do this work, but the idea is just that you have a 2-stage problem. So at one stage, you optimize, for a given architecture, you optimize your weights, and then in another stage, you try to change the architecture a little bit. And so you go back and forth until you converge. And this strategy, it's kind of automatic machine learning. You don't need the person to select an architecture. Everything is done automatically. And I mean, what I've heard, I've just heard the seminar on this and read the paper. They typically find an improved performance when they do this. And so the meta parameters that are just parameters that identify different architectures. So that's the idea. Yeah.
There was another question? Yeah. Yes.
You say that cross entropy should be interpreted as a robust dynamics by minimizing the cross entropy losses, or it's equivalent to minimizing perform a dynamics which is robust, starting from the error boundary. But what about the mean square error? Because we have seen that also in that case, for the mean square error loss, you have this big flat region as well, similar to what as the concept. Can you establish the same connection and maybe motivate with this robust dynamics, the mean square error, or maybe it's another reason that is as you are developing this flat region?
There is the problem of in the case of the mean square error, you probably use sigmoid transfer functions, right? Yeah. So these sigmoids also contribute to the nature of the minima. So we didn't analyze that in specific. Just we essentially, to be honest, we skipped completely the study of that. We just did some few numerical experiments. We didn't do any analysis. So it should be done, but we didn't have time.
In that case, you also like invariant that you have this like.
Yeah, but it doesn't work as well as cross entropy. So kind of but it's just a amount of energy we had. We didn't have time, but yeah, it could be very interesting, yes. No.
Yes, please.
Yeah.
Yes.
You seem to be getting different answers than Ganguly. That is, you say ReLU is more robust. He says Tanch or smooth transfer functions are more robust. Are you asking the same question?
Probably not. I mean, this is a calculation, so I mean, it should be correct. I think we are talking about different properties.
I think they're actually mutually consistent because I think I was talking about the initialization and speeding up
Oh, yeah.
part of the learning curve, and you're talking about where you end up.
Yeah.
So actually annealing the nonlinearity might be an interesting approach.
Yeah, we can show that that really gives you. Yeah.
This does get complicated.
I don't know. Okay.
Any other question? I have one, actually. In the point you meant the open problems, let's say,
Yeah.
the interesting problems.
Yeah. Well, what example
yeah,
of?
okay.
Yeah.
In your opinion. Okay. Can you explain a little bit more what you mean with the causality through
Yes.
invariance? Because
Yeah.
I did not understand.
This is very. I recommend a talk by Leon Bottou. You can find online on this problem. The idea is that suppose you have an apple that falls from the tree, but you have many data about that. But you have data during the day, or during a rainstorm or whatever, different. So, for instance, typically you have data, pictures that are taken during the day. So there's some trivial correlation, like light and the fact that the apple falls down, which can affect your learning. So the idea is, if you have different realizations of your physical law, I mean, whatever you want to extract. The issue is, can you extract what is invariant among the different realizations? And this is going to give you information about causality, so the law that governs the data. So that's more or less, it's a very, very complicated problem from the optimization point of view, but I think it's a beautiful idea because you get rid of all these logical networks to explain things. This is just a matter of invariance. Yeah.
So, thank you very much, then. And so. So let me thank all the speakers of the conference and the organizers and all the community of the Replica Symmetry Breaking. I think maybe, I don't know, maybe Giorgio, you want to add something as a concluding?
Well, I would like to thank again all the other organizers because, as I told you yesterday, I wasn't the organizer list, but I not done too much work. And of course, we had a very strong input from the local organizer, Fernanda, and also Gabriele Securo, that take care of all practical questions in the organization. Gabriele, of course, also scientific one. We are very grateful to all people that came here and all people that spoken. Although that there was some suggestion, I think, by Berthier, we will not have a Replica Symmetry Breaking 41. That for sure, because we need at least 10 years of or rest before organizing a new one. Something that we were started thinking that we are going to write to the speaker, if we could have a volume of some review with the talks of the speaker. Of course, this implies that the speaker should write something. But if we have, we'll write to the speaker, and if we have a sufficient number of positive answers, I think that this would be nice things, because also some talks were of a review of the subject, and I know that the speaker have used a lot of work in preparing this review, so it may be nice to have this written somewhere. So that we will write to you about these things to see your reaction. So again, thank you to everybody.